Swayam Prabha. Digital India. Educated India.
Okay, dear all, as you know the different kind of devices I am going to show you in this lab course. So, I taught you many devices in this class. So, now let us see the actual how they looks like. See, at the very beginning of this class I showed you the glucometer. See, this is the glucometer and this is the glucometer chip. So, as you know, in this glucometer, here we will drop the sample, then we will insert this one in the glucometer and we will see the reading here. Why it is not showing now? Because we will drop the blood sample. So, just for demonstrations, it is looks like this. This device, this is just a portable electronic device. It can measure the data. So, in this course, in the lab class, my students already showed you how to design this kind of portable device. So, this is just commercialized this version. And now, let us come how we can devise similar kind of thing from the lab. See, this is commercially available 3 electrode system printed chip, you know. So, this center side is the working electrode, this semicircle black one is the counter electrode and a small this semicircle is the reference electrode. So, this is commercially available. Similar kind of electrode we can design for different kind of disease diagnosis. So, not only like the glucose, different kind of other analyte can be detected, that I taught it in the class. So, let us show you this all the electrode how we can use in the lab setting for fabrications of the different material. So, last class we showed you the synthesis of nanoparticle. So, we can drop cast here. So, this material, suppose you synthesize some gold nanoparticles or something else, that you can drop here. Then we can insert, instead of this chip, we can insert this chip here, same technology. Instead of glucose, you can detect another analyte. You understand the technology here, right? Very simple basic things. Now, if it is a cancer detection chip, it can detect cancer. This is the main basic principle. Okay. Another commercially available very recently, this is very important, COVID self, commercially available that can detect COVID. You can see, I think I taught you the colorimetric sensors also, right? So, we bought this one from the market and as I told you, similar kind of things you can also design. See here, I taught you already this kind of colorimetric sensor, like pregnancy test kit I taught you, like you can drop the sample here, then this is the microfluidic, like paper based device. So, it will flow through this paper. Then see there is a 2 channel, one is test, another is the control. So, if you have the COVID virus, then it will show the test zone color and control zone also. And if you do not have, then control zone will show the color, test zone no. So, that principle I taught, right. So, you see this is the actually device. So, it is available in the market. As I taught you the basic principle, you also can design now, not only the for COVID, because it is already in the market. You can think about something other also device, right, and you can bring in the market, you can start your startup, right. I told you already. So, let us think from the lab itself. Now, you are ready for this making a new startup for your own. Okay. Something else like I taught you many times, like indium tin oxide coated glass electrode, there we can use many sensors. See, this is the actually very simple glass chip. See, it's very cost effective, very simple. You can see here, right? And it's very robust. See, I'm just touching this surface also. It's very robust, this chip. After cleaning, that I taught you, no, but while you will deposit the material, that time you should not touch like this. But now I can touch also. But after cleaning the surface, then you can drop your all the material here. Then you can use for the sensor development. Many times I use the indium tin oxide coated glass, right? This is actually the chip. This is very simple and robust chip. And printed circuit board. Many times I told you, no, PCB based biosensor. See, this is this kind of chip already available, right? In the electronics, if you open any electronics, any kind of instrument, if you can see this kind of board, this is the printed circuit board. See here 1, 2, 3, 4. Here multiplex detection you can go. So here one detection, here another, here another, here another. So 4 channels are there. See, here is the connections. Here is the another like circuit connector. Here you can connect it, and then this one actually you can connect to your portable device. Something like this, a portable device. It can be connected. See, this is a very handy, simple, right? That's I told mobile phone based. It is right now it is separate, but same thing you can insert not like here to your mobile phone. Then inside the mobile, when instead of using this one, then your mobile phone will be your display, right? You can see the data on your mobile phone, right? It's clear. Now let's again come to the very basic lab setup, where I will show you to develop the signal amplifications. See, I taught you signal amplification strategy like electrochemical, chemical redox cycling for getting high signal to background ratio. Why we need high signal to background ratio? To detect the disease very early stage. So let's see the, for example, electrochemical, chemical redox cycling, how it works. Now I will show you one example of ECC redox cycling, and you can understand how you can amplify the signal. That technology you can now use the chip and get the new device, and you can think about your own startup. Okay students, now I am showing you a very basic electrochemical, chemical redox cycling, how to take. So today I will show you the ECC redox cycling with ruthenium, hydroquinone and T-shape, these 3 combination based. So let's see how the signal amplifying based on this ECC redox cycling. So I will take first 1 millimolar ruthenium hexaamine. See, this is just a buffer. So here I am taking just PBS phosphate buffer saline, and I will dilute this ruthenium salt already prepared. See, here I covered the ruthenium salt with aluminum foil because this is light sensitive. So here we prepare 10 millimolar ruthenium salt. What is the ruthenium salt? This is ruthenium hexaamine. Here ruthenium oxidation state is 2. So it is reduced from ruthenium. So it is 10 millimolar. So I will take 1 millimolar here for getting a cyclic voltammogram. So here 100 microliter. So I will take from here 100 microliter of no. So at first let's take the 1 ml. So I will take 1 ml ruthenium hexaamine 2 salt. So I am now mixing properly. So see, here I took 9 ml phosphate buffer saline buffer and 1 ml ruthenium 2 salt, that is 10 millimolar. So here you can understand now total volume is a 10 ml. It means the ruthenium 2 salt concentration is now become 10 times less, means 1 millimolar. Okay, now let's check the cyclic voltammogram in this solution. So where I will take on a simple glassy carbon electrode that is already cleaned, that we showed you last class how to clean this surface. Then after cleaning, so this is the working electrode. I am going to dip into the solutions. Here silver chloride reference electrode. And so we will measure the potential difference based on silver chloride. Here platinum counter electrode. Okay. So your 3 electrode setup is ready to take the cyclic voltammogram ruthenium hexaamine. See, I am now, we have to dip inside this solution. So 3 electrodes should be dipped properly. Now let's connect. So like this way, we are actually handling the electrochemical workstations inside a lab. This is the very basic setup of 3 electrode system. See, so this one for the working electrode, this red one is for counter electrode and connecting, and this white one for reference electrode. So it means, see, they all electrodes are dipped and they are connected each other. So now we are ready to take the cyclic voltammogram. So here is the ruthenium hexaamine. So it means the oxidation state is the 2. So I have to start from the left side negative to right side positive, means it will first oxidize 2 to 3 and then 3 to 2. So that's why I fixed the parameter. Initial parameter is minus 0.4, then I fixed 0.6 as a positive, because I know that ruthenium hexaamine oxidation peak will show in between. So accordingly we have to fix the parameter. Okay, now let's run the cyclic voltammetry in this solution. So at the beginning you can see quiet time, so we put some time, then the cyclic voltammeter will start. You see, so it is oxidized here, and further just see, just you will get just some lines, means it will not show any peak here. Why? Because ruthenium property is this oxidation will show only this region around minus 0.1. Here you will show the oxidation, and then you will see the reductions here. Okay, so see, so this is just for any kind of, see, this is also good that you got some another small hump. This is just for maybe if you have any impurity in your surface or your solutions, because this electrochemical sensor is very sensitive. So you may get this kind of peak. So why? Maybe some kind of impurity if you have, then it's good that you can see something. But if there is no impurity, your surface is properly clean, your solution is very clean, very pure, then you will get only this peak and then reduction peak. And see, they are very much reversible. This oxidation peak and reduction peak, they are very close to each other. Okay, so at the very beginning for the ECC redox cycling that I taught you, you have to take first this electrochemical signal for the background. So your ruthenium hexaamine, your basic background. But you are taking the 3 combination, right? Ruthenium hexaamine, hydroquinone and T-shape. So what is your background then? Ruthenium hexaamine and T-shape is your background. So let's take then T-shape plus ruthenium hexaamine, how much they are contributing on the background. So let's check the another cyclic voltammetry. Solution mixture will be ruthenium hexaamine 2 and T-shape. So now I will take ruthenium hexaamine 2, this solution, and T-shape. So as I told you, how to make these actual different concentrations of this solution, right? I told you that I made 10 times higher the concentration. Ruthenium hexaamine 10 millimolar, T-shape 20 millimolar. So but I am going to take 10 times less. So how I will dilute these solutions? Let's learn this one. So I will take 8 ml buffer, that is phosphate buffer saline, inside the electrochemical cell. So here 4 ml and then another 4 ml phosphate buffer saline. Okay. Then I will take 1 ml ruthenium hexaamine. This is ruthenium hexaamine 1 ml. So but always just try to remember, while you will take from a stock solution, just don't forget to shake it properly. Just properly you should make the homogeneous solution. So take 1 ml ruthenium hexaamine and put in the electrochemical cell, as pipetting few times to make the homogeneous, and then I will take T-shape, that is a reducing agent you need, because this ruthenium hexamine and T-shape is responsible for your the background current of your ECC redox cycling, right? You just remember. So what you will do, just shake it properly and take 1 ml from the stock solution and put inside the electrochemical cell. Okay. Now what I will do, I will again we will make the homogeneous solution. You have to pipette it out for few times, so that your solution become homogeneous. See, now the final volume is the 10 ml, 8 ml buffer, 1 ml ruthenium hexamine and 1 ml T-shape. So final concentration now ruthenium hexamine become 1 millimolar and T-shape become the 2 millimolar. They become 10 times less. So again I will put that I already made this 3 electrode setup. So working electrode. So let's put this 3 electrode system back to this cell. So let's dip inside this solution. So now this solution is responsible for your background current, right? So in the same potential window you can see here. Okay, so this is ruthenium hexamine CV only. So I save this data in my computer, CV ruthenium. So it's saved already. Now I will take the background of this ECC redox cycling. So background means ruthenium hexamine and T-shape. So this solution is ready and we will use the same parameter. We will not change the parameter. Otherwise you cannot compare. So in the same potential window, let's see the cyclic voltammetry in this mixture. Okay, then we will compare with this CV and only ruthenium hexamine. So as you know, if you want to design a very good ECC redox cycling based biosensor, so your reducing agent should not react with your electron mediator, right? So that's why I want to compare ruthenium hexamine CV and ruthenium hexamine plus T-shape CV, and you will see there is not much change. That I taught. Let's see practically how much change you will get. Okay, so this CV done with the T-shape, that is actually your background. So let's save it. So this one ruthenium and T-shape. So we are just saving it. And let's I will overlay this one, graphics, new overlay, only ruthenium. See, you can see, let's change the color here. Okay, you can see here the two different cyclic voltammogram. Like one is just ruthenium and another this one only ruthenium T-shape. So there is not much change. See, almost they are similar. It means ruthenium hexamine and T-shape, they are not reacting each other. That's why you are not getting much difference. Also, we can take like chronocoulometry, chronoamperometry as I told you to get the signal differences, but which potential we will choose. So as I taught you, first we will take the cyclic voltammetry, then we will decide which potential is good for chronoamperometry or chronocoulometry. See, here oxidation complete after this potential, right, minus 0.1. So we may take little higher, where we will get the maximum oxidations, or we may get the complete oxidations of the ruthenium, right. So we may choose 0.1 this potential, but the optimization potential I already taught. So you have to go through different potential, then you have to find out best potential for highest signal to background ratio. So for example, now I will choose minus 0.1 for getting chronoamperometry. So I will go to the chronoamperometry and 0.1 potential I will choose. So your highest will be 0.1 and initial that can be and we will oxidize this solution. So, let us make it positive. So, total step we will take 1 and we will take just for 30 seconds. And the sensitivity means we are using. Okay. So, let us see. Now, we are checking in the same solutions how the chronoamperometry it looks like. Then we will compare this background data with the signal data. Now, you are getting the background data at 0.1 volt. Then we will compare at the same potential with your signal data, that is ruthenium, T-save and hydroquinone, that I am going to take after this measurement. Okay. So, this is your background data ready. So, I will save it for your comparison. So, this is chronoamperometry and this is your background. Okay. Now, let us go back again the cyclic voltammetry with actual signal data, that is ruthenium hexamine, T-save and hydroquinone. Okay. Now, again I will prepare the solutions, that is responsible for the signal. So, similar way I will take first the buffer. So, first I will take 7 ml phosphate buffer saline, then 1 ml ruthenium hexamine, 1 ml T-save and 1 ml hydroquinone. So, final your mixture, each component will be diluted for 10 times, right. So, let us take. So, I am taking first phosphate buffer saline PBS 7 ml. Now, ruthenium hexamine. So, as I told, just mix it properly and then put 1 ml. Then 1 ml T-save. I am just pipetting in, pipetting out for making homogeneous, or you can shake it, and then here again I do. This is the T-shape one. Then I am taking the hydroquinone solutions. See, again you can see here all the solution I wrap with aluminum foil. If you have any solution light sensitive, then let us try to keep them stable by wrapping with aluminum foil, so that you can store your solution for longer time. Now I am taking the hydroquinone. So, I will make this solution again homogeneous. So, let us make so that each solutions will homogeneously will be diluted and you can get the reproducible data. So, now your solution ready. I will dip all the electrodes back to cell, the working electrode, counter electrode and reference electrode. Okay. So, your cell now ready to take the measurement for your signal data. Okay. Now, I will take first cyclic voltammogram. You see that I am using the same potential window. So, this is your background. Now, take the signal data. So, you can see the same parameter I am using. So, let us take the cyclic voltammetry first inside this solution. Okay, your cyclic voltammeter ready. Now I will compare and I will explain the the distinguished peak. So let's overlap. So this is your signal. Let's compare with the background CV. So ruthenium T-shape. You can see that here characteristic peaks come here. This is due to the hydroquinone, and in the ruthenium side you can see the kind of the signal amplification not much. This is because the 3 solution was not reacted properly. So why it is not reacted? Because ruthenium hexaamine, T7 hydroquinone, they should interact with each other. So we need some incubation. So I just drop it and take it. I took it immediately. So let's incubate for some time, and then I will take again the cyclic voltammetry. Then you can see the change. So it means these 3 reactions was not completed. So I will incubate it for 10 minutes. Then I will show you the difference of the cyclic voltammetry. Okay, your 10-minute incubation now already done. Let's take the cyclic voltammetry. Then I will compare after this incubated solutions and non-incubated solutions, background and signal value. And then I will take chronoamperometry, then we will compare background and signal. Then you can learn how we are comparing the background signal and your actual signal value. And if your scheme work, then you will see the difference. If your scheme does not work, you will not see any difference between the signal and background. So as I mentioned, this is because of your hydroquinone and this is because of your ruthenium. So let's save this one, this data. So this is your CV for signal. Okay. Okay. So you see, this is the 2 distinguished peak, hydroquinone and your ruthenium. So they are actually reacting each other. That we can observe if we take the chronoamperometry. So let's compare here. Just only your see. So still. See, it means, okay, you can see here is not that much difference. Your difference came actually this side, and we want to check their reactions actually more than your ruthenium potentials, and actually we have to find out which potential is best for this reaction. So you can see if you take the potential near the negative side, there is not much amplifications. So you have to take the optimal potential near this window. That's why optimizations of ECC redox cycling is also very, very important. So let's take, that's why first chronoamperometry. So I took the background in 0.1, then I will take the signal also at the 0.1. So let's open your background. So this is your CA of your background, and we applied 0.1 volt, and same potential I will apply for signal. Let's see. Okay, your chronoamperometry done. Let's save this data. So this CA for your signal. Save. So I will teach you today how we can convert this chronoamperometry to chronocoulometry. We can convert these things also at the same time, But let's compare first the chronoamperometry with background and signal, then again I will compare the background and signal with chronocoulometry also. So let's overlay the data with the background data, CA. Okay, so you can see there is a difference, right? So this is the signal data and this is the background data. So if we see, if you want to make, if we zoom this area, okay, now so you can see actually the difference in the signal and background. Okay, so but one thing, why I taught you the chronocoulometry also. Chronoamperometry case you are getting this much difference, but you can convert it to the chronocoulometry and you will get the much better difference than the chronoamperometry. Because why we are getting the better difference? Because we are actually integrating the current, right, in the chronocoulometry. That's why you will get the much better difference. Let's show you here. So your signal and background difference is there, means your scheme actually working. So let's open your background signal CA of this, then you can integrate it. Integration, say here is the option is the integration. You can integrate it and you will get it the chronocoulometry. So that's why you don't need to take the separately the chronocoulometry, and we can integrate the current of the chronocouloamperogram and you will get the chronocoulogram. So this is basically your background. So let's save this one. CC background. Okay, and now we'll open the signal value of your chronoamperometry. So this is your chronoamperometry of the signal. So we can, that's as I mentioned, just we can integrate this one with the software and we will get the chronocoulogram. So let's save this data. Signal, let's save it. Okay, so let's compare now background. CC of the background. Okay, so see here is the difference is there, like background and signal. But one thing I wanted to tell you, this difference is not enough still. So there may be some issue can be there. Your reagent cannot be good. If you want to get the better signal, you have to optimize the concentrations of your reagent. Different concentrations of the reagent may give you the better these amplifications, as I taught you in the class. And another optimizations you may need, that is your very important optimizations, that is the potential. You can see I choose here 0.1, then I got that much difference. But if you compare your reactions with your signal and background and your signal CV, your CV of ruthenium, CV of signal. See, its difference is coming, but your actual difference is actually is much better in this region. So you can choose much higher potentials also for getting the much better signal to background difference. See, accordingly you can optimize the best potential for your ECC redox cyclings. So that's why, see, here is not that much difference, but actually hydroquinone and ruthenium can take part maybe this region, that you have to optimize and you may get the better signal to background ratio. Okay, so that's all for the ECC redox cycling, and I think you learn now all the theoretical demonstrations